So this is our video 3, and I'm going to cover some mathematical preliminaries here. I had mentioned that I won't use slides, and here I am using slides, but what I've essentially done is draw things out the way that I would draw them on the whiteboard. So we'll talk through it like this, and if I'm doing this right, the mouse should be highlighted. Before we start, I'm not trying to teach this. I'm just trying to jog your memory. And remember, if this isn't ice cold to you, that's okay, don't panic. I just want to convey the material that we're going to be using, the math fundamentals we're going to be using all semester. And that's why the math refresher is so important that I gave you to do, because you can see where you might need to focus some energy to harden your math skills. Alright, so math preliminaries. We'll start with trig functions. I have a right triangle here. I've drawn an angle theta. You can see the side opposite I've labeled O. It's opposite to theta. The side adjacent I've labeled A because it's adjacent, and we have our hypotenuse H here. Most of you have probably heard the word, maybe all of you, SOHCAHTOA, and this is basically a nonsense word that reminds us of the basic trigonometric identity definitions. The sine of theta, S, is equal to the opposite over the hypotenuse, which basically means if I wanted the sine of this angle theta, it's this side, O, divided by H. Cosine is equal to the adjacent over the hypotenuse, and the tangent of theta is equal to the opposite over the adjacent. So if I wanted the tangent of theta, I would divide the length of this opposite side by the length of this adjacent side. Some key trig identities is sine of theta over cosine theta is equal to tangent of theta. Sine squared plus cosine squared is equal to 1. And this is one you might not have seen too much, the double angle formula. This isn't the general form, it's somewhat of a specific form. But it'll come in handy. So the sine of 2 theta is equal to 2 sine theta cosine theta. Now, the sine and the cosine functions look essentially like this. And they're both derived from the unit circle. The sine function is shown in black, the cosine function is shown in red, and essentially they're shifted 90 degrees from each other. But they both peak at positive and negative 1. And you can see the sine function, they both have a maximum height of positive and negative 1. The sine function reaches that maximum positive height at 90 degrees, whereas the cosine function starts with that maximum height at 1. And you can see where they cross the 90 degree, the 180 degree, the 270 degree, and the 360 degree mark. Now, we work in degrees for angles sometimes. We're also going to be working in radians. And you may remember the definition of radians. There are 2 pi radians per every revolution, or thought of another way, there are 2 pi radians for every 360 degrees. So it's equivalent to say that 90 degrees in an angle measure is equal to pi over 2 in a radian measure. 180 pi, 273 pi over 2, etc. We're going to be using these functions all the time, and it's important to understand what they look like, where they do their crossings, etc. A useful thing, I misspelled this, the sine of an angle is equal to the cosine of its complement. And if we go back to sort of that right triangle that we drew earlier, I now have the angle alpha over here. And if we remember our definitions of sine, what's the sine of alpha? Well, it's the opposite over the hypotenuse. So in this case, it's y over h. Sine of alpha is equal to y over h. Now the complement of an angle is the angle that you would add to get 90 degrees. So because this is a triangle, I've got a 90 degree angle here, alpha and this angle beta have to be complementary. They have to add up to 90 because there's always 180 degrees in a triangle. So the sine of alpha, is it really equal to the cosine of its complement beta? Well, we know the sine of alpha is y over h. We just did that. What's the cosine of beta? Well, we go here. Cosine is the adjacent over the hypotenuse. The adjacent side to beta is y, and the hypotenuse is h. So sure enough, the cosine of beta is y over h, the sine of alpha is y over h, so the sine of an angle equals the cosine of its complement. Pythagorean's theorem everybody knows and loves. A squared plus b squared is equal to c squared. Or if you like, c is equal to the square root of a squared plus b squared. And the quadratic equation is incredibly useful. I was about to say we're going to be using that a lot, but everything I'm showing here we're going to be using. So if you have a second order polynomial function, second order means square, polynomial function like ax squared plus bx plus c is equal to 0. You draw it out in this form. So you have these coefficients, a and b and c. Then we can use our quadratic equation. right? Negative b plus or minus the square root of b squared minus 4ac over 2a. And out will pop two values of x. And this works generally. Now, in math class, you've also learned about factoring. Factoring works as well, but not all the time. In fact, a vast minority of the time. So here's an example. X squared minus 3x minus 4 is equal to 0. And I've written it in this form so that our coefficients pop right out. So the coefficient a is 1x squared. The coefficient b is negative 3, not 3, negative 3. And the coefficient c is negative 4. I can pop those right into my quadratic equation and get my two answers for x, my two roots. I'll find that x is equal to 4 and x is equal to negative 1. But fortunately, and in this case, a rare case, this factors as well. So you can convince yourself that this factors to x plus 1, x minus 4, and you get the same results. Some circle facts. Circumference of a circle, 2 pi r. The area is pi r squared. A less commonly known one is the volume of a sphere, 4/3 pi r cubed. All good things to know. And these are the kind of equations, by the way, that I would give you on an equation sheet, okay? Slope of a line, generally speaking, y equals mx plus b. So what I've drawn here is an xy coordinate axis set, if you will. And I've drawn the line specifically y is equal to x. So it's a nice linear function by definition, really. And if we write this function y equals x in this general form, it would be y equals 1x plus 0, right? I don't have that written out that elaborately here, but that's what it boils down to. Y equals 1x plus 0. There's no value of b. B represents the y-intercept, and sure enough, it crosses at 0. So there's no plus 0 here. That would be a little redundant. The slope is 1. For every value of x, like x equals 3, this line is going to result in y being equal to 3. The slope is equal to 1. And the general equation of slope, very important, change in y over the change in x, or more specifically, y2 minus y1 over x2 minus x1. Now if we generalize that just a little bit for you calculus people, the slope of a function more generally, and specifically a second order function like this, what I've drawn here is a parabola, a concave up parabola, and the function is y equals x squared. So it's nice and it's symmetric and it crosses the y-axis at 0. But what does it mean to have a slope of something like this? For the straight line case, it's pretty straightforward. It's a straight line. It's got a single slope. For a curve, though, the slope comes into play depending on where on the curve you're interested. So I've drawn 2 points here, one at x equals positive 1, the other at x equals negative 1. And I can actually draw 2 different tangent lines. These are completely different tangent lines. They have very different slopes. To find the slope of a polynomial like this, you need to essentially do a little bit of calculus. So I don't have it written here, but you would take the limit of delta y over delta x, just as we had before, as delta x gets smaller and smaller and smaller. And we call that limit, as it goes to 0, in fact, we call that limit a differential, dy dx. Now for those of you that have done some differential calculus, you know that you would take the first derivative of x squared, and that would be 2x. If you haven't seen this before, that's fine. It's not hard to do. It'll be trivial once you know how to do calculus. But for now, just take my word for it. The derivative of x squared is 2x. And what that means now is I've got a general function, 2x, that gives me the slope of all tangent lines to this curve. So if I wanted the slope at x equals 1, I would use my first derivative, 2x, and I would pop in x equals 1, and lo and behold, the slope is 2. At x equals negative 1, I get a very different slope. 2 times negative 1 in this case is negative 2. And finally, my last, so to speak, slide, we're going to be solving systems of simultaneous equations a bunch. And what I mean by that is we might end up with something like a plus b is equal to 6, and then another equation, something like 3a minus 5b is equal to 9/10. And you've got 2 equations and 2 unknowns, and you might remember back from algebra or algebra 2, there's a couple of ways to solve that. So we'll be doing that. Sometimes we'll have 3 equations and 3 unknowns. Algebraic manipulation all the time. We'll be living and breathing this stuff. So Here's a nice little equation. We've seen this one, y equals mx plus b. So if we needed m, well, you can just rearrange things. And I did it all in one step here. But, you know, you subtract b from both sides, and then you divide both sides by x. And so I'm simply rewriting this. Scientific notation again, all the time. I've got an expression here, c is equal to 3 times 10 to the 8th meters per second. And so what that effectively maps to is that we've got 8 zeros following that through 300 million meters per second. And some of you may know that c is a special number that we use in physics, and that's the speed of light in a vacuum. It's a very important number. E equals mc squared, that's the c. And the second example down here, a little bit bigger, 6.02 times 10 to the 23rd. Well, here we've got 23 places to the right of that decimal. So we're going to have 21 zeros following the 2. And some of you may recognize this from chemistry. This is Avogadro's number, the number of molecules or atoms per a mole of a substance. So this is the map that we'll be using, and I'm going to repeat myself. Don't panic if you don't know this cold. This is what the math refresher is for. In the next and final video, I'll cover Chapter 1.